Yeah, I'm happy to introduce our speaker today, Neal Dalal. We were fortunate to have him here for the whole week, so I think most of you have had a chance to chat with him at this point. Plus, I'm visiting us from Perimeter. Before that, he was in Illinois at UIMC. And before that, he spent some time at CETA and then here at the Institute. He is maybe most well known for his work on large scale structure and understanding what that can tell us about neutrino physics, about inflation, but is generally interested in cosmology and has a wide range of interests, including astrophysical probes of dark matter, gravitational lensing. And the topic he'll tell us about today is maybe a new spin on an old interferometry technique. So either way.
Okay, yeah, great. Yeah, thanks, Debbie. Yeah. And thank you all for hosting me. So this visit so far has been lots of fun so far. Yeah, so today I want to tell you guys about this idea we've been working on, related to interferometry and also maybe black holes. This work is done with a bunch of people. The main person I want to highlight is our postdoc, Marios Galanis, who's just great. These are all hire him. And then these other guys are also decent too. They can hire them too if you want. Okay, so the basic idea I want to talk about, a thing that we've been thinking about, is how to use intensity interferometers to study AGN, supermassive black holes that are bright because they're rapidly accreting. I'll discuss some possible applications of this, some of which we think are, are pretty exciting. And if there's time also, we can discuss things besides AGN because, high resolution imaging, of course, is useful for many, many different areas. Okay, so just to put everyone on the same page, let me first just remind you all of some very basic aspects about interferometry. Okay, so we'll start off just by reviewing things that you've already seen about radio interferometers. Okay, so the way that radio interferometers work is that we have multiple radio telescopes, and each one records the oscillating electric field that it receives. We then take those recordings of the electric field and correlate them with each other. And that correlation, called the visibility, measures for us the Fourier transform of the brightness of the sky by the famous Van Surder-Zernicki theorem. Okay? Right, so we correlate electric field by two different locations, and it measures for us Fourier transform of the sky. So if we measure the Fourier transform at many, many different points on the Fourier plane, we can then reconstruct what the sky looks like. And the angular resolution with which we can do this, of course, is just set by the usual lambda over b, where lambda is the wavelength of light that we're observing, and b is the baseline, the separation between the different telescopes. Okay? So, for example, the famous Event Horizon telescope, so they observe at millimeter wavelengths, and they have baselines the size of the Earth. And so taking the ratio of these two numbers gives an angular resolution, something like 20 microarcseconds, right? So just amazing, And so with that fantastic angular resolution, they were able to, to make these pictures of the black hole at the center of our galaxy. Now, those pictures that they gave us had like a few pixels across the horizon. And so, of course, they want to do better than that. They want to have even better angular resolution. And so some of you, perhaps have seen or perhaps are even part of, these proposals to do EHT in space. This is called, so this Beck's proposal. So they want to get better angular resolution by going to space to increase the baseline. But you can see that, so another way to get better resolution while staying on the ground just is, to observe at shorter wavelengths. So for example, visible light has wavelengths many thousands of times shorter than radio wavelengths, okay? And so in principle, for the same baselines, if you could do interferometry at visible wavelengths instead of radio, you could get, in principle, thousands of times better angular resolution. However, however, there's a challenge in doing this. Because the wavelength is thousands of times shorter, the frequency is also thousands of times higher. And so in practice, there's just no practical way to record the electric field at visible frequencies, preserving the oscillation. Okay. So therefore, therefore we cannot do optical interferometry the same way that we do radio interferometry. And so instead, a different method is used. Okay, so it's done for these optical interferometers is that we have multiple telescopes. And then we actually physically combine the light beams from these different telescopes. Okay. These combined light beams interfere with each other, producing interference fringes. And the contrast of those fringes measures the exact same visibility measured by a radio interferometer. Okay, so we get the exact same Fourier transform of the sky. It's great. But of course, there's one drawback. Because we are physically combining light beams, this then limits how widely separated the telescopes can be. And so in practice, the longest baselines for which we've done optical interferometry have been less than 1 kilometer. And so even though the wavelengths are thousands of times shorter, yeah, the baselines are also thousands of times shorter. And so therefore, the angular resolution in practice isn't any better doing visible interferometry compared to radio interferometry.
Why is this baseline an issue in optical? Is it just like transferring the light across that baseline with the velocity process, like the fiber optic cables aren't good enough or something like that?
Exactly, that's right. Yeah. So yeah, exactly, that's right. So you can imagine, so you can imagine amplifying, but in general, amplifying loses phase coherence. Yeah. Yes, this is why. There are some proposals to extend this all the way up to like a kilometer using these extremely low loss fibers. But even then you get like 40 dB of loss in the fiber. So yeah, so yes, this is hard. Right, okay, so therefore, right, we don't get any better using normal visible interferometry compared to radio. Now this compared to like VLBI. Okay, good. So all of that is familiar, regular amplitude interferometry is called. Now, it turns out that there's another kind of interferometry, developed back in the 1950s by these two guys, Hanbury Brown and Twiss, and it's called intensity interferometry. And this works on a somewhat different principle, okay? And so instead of correlating the electric fields received at two different telescopes, we instead correlate the arrival times of single individual photons as they're coming into the two different telescopes, okay? And so the statement is that even for telescopes that are separated, photon arrival times are correlated with each other. That is, photons reach us at times that are bunched together. Okay, so that statement might seem surprising. And so to see why that happens, let's just go through some simple examples. Okay, so we'll start off at the most basic level. Okay, so suppose that we have a monochromatic source of light. Okay, some source for which the E field just oscillates in time, like this, constant frequency, constant amplitude. Okay, the intensity is E squared. Okay, so it's the envelope squared of this oscillation. And so if this coefficient up front is constant in time, then the intensity is constant in time. Okay, good. Now let's do two monochromatic sources of light. Okay, so suppose we have the omega-1 and also omega-2. All right, and let's suppose that these two frequencies are not exactly the same. Okay, so suppose they're, so suppose that they are close to each other, but not exactly the same. And so if I add up two oscillations at slightly different frequencies, what do I get? Do people remember? Sorry, I can't hear you. Gold star for you, Yvonne. Yeah, that's right. Yes, we get a beating oscillation. Okay. Right. So the electric field oscillates, and so you can see that it has these two time scales in it. So first we have fast oscillations that are happening at the central frequency, i.e. the average of these two frequencies that we're adding up. And the envelope of these oscillations also itself oscillates in time, with the frequency given by the frequency difference. Good. That's the E field. The intensity again is the envelope squared. Okay. And so the intensity oscillates up and down again on this time scale given by the difference in frequencies. Good. So now let's do the most general case where we're summing over many, many different frequencies. Okay, let's say drawn over some, some range, some bandwidth of frequencies. Okay, so what do we get? So we get the exact same thing. Okay, so again, we have, the E field oscillating with these two characteristic timescales. So first, again, we have fast oscillations that are happening at the central frequency, with the central frequency, you can think of it as just something like the average or the midpoint of this band that we're summing over. And then also the envelope also fluctuates up and down randomly in time that, okay. Again, on a time scale that's given by the scatter in frequencies, i.e. the bandwidth. Good. So again, that's the E field. The intensity is again the envelope squared. And so we can see that the intensity is oscillating up and down, fluctuating up and down randomly. Okay, again, on this time scale given by the bandwidth. Okay, so I want to drive home that we get these order 1 fluctuations in the intensity, even when the source is completely constant in time. Okay, so even when all these coefficients are exactly constant in time, we get order 1 fluctuations in the intensity of the source just from the interference of these different waves with each other. Okay, good. So these fluctuations in intensity then give us fluctuations in the rate at which we see photon counts. Okay, obviously. Okay, so at times when the intensity is high, there's a high rate of photons reaching us, and at times when the intensity is low, there's a low rate of photons reaching us. Okay, I want to stress this is not Poisson noise, this is not shot noise. Okay, so even when the number of photons is huge, so for example, so at radio observations, or the number of photons is basically infinite, and therefore Poisson shot noise is 0. Okay, we still get order 1 fluctuations in the rates at which photons come to us. Okay, good. So this is the origin of that bunching effect that I described. So is that clear for everyone?
So this is a purely classical effect.
The way I'm describing it is purely classical. You can fully understand it classically. Now, as Hanbury Brown and Twiss discovered to their dismay, quantum theorists didn't like this explanation, and several luminaries at the time informed them that they were obviously wrong about this. This measurement would, it would seem that this would violate quantum mechanics. And so Hanbury Brown and Twiss's proposals got rejected in the States, forcing them to build their telescopes in Namibia or something, I think. Right, and so eventually then famous people Purcell or Glauber had to explain to everyone how this all makes sense quantum mechanically. But I like the classical explanation because it's simple to understand and it gets you everything about this that's relevant for astronomy. Good. Okay, good. So, right. So, yes, this is not Poisson noise. We generically get these order 1 fluctuations in the brightness intensity of our sources for any broad band.
What if the Fourier transform is not sum of deltas, but some of the function?
Yeah. So okay, good. So this example that I'm showing you here, this is for a top hat spectrum, continuous spectrum. Okay, right. I explained it as a sum, but that sum becomes an integral in the continuum limit. So a black body does this. Good. So again, order 1 fluctuations.
But then the delta omega, what is the delta omega in that case?
Is the bandwidth,
Okay.
the scatter in frequencies that you're summing over.
Can you still apply this sort of technique if you do have substantial Poisson fluctuations, right? Because if you could go to X-rays, that gives you a very small wavelength, but then you are limited by photons.
Yes, and so I will describe maybe in 2 slides or 3 Poisson noise. Yeah. Because of course, for any optical source, we do have significant Poisson noise. Yeah, so hold that thought. Okay, where was I going? Yes, okay, so we can use these intensity fluctuations to do interferometry the exact same way that we use the normal EVI omega t oscillations to do interferometry, okay? Using the exact same reasoning. So suppose that we have some source over here shooting light at us, okay? Producing this, so this E field with these waveform, suppose that it's seen by our telescope. And suppose we have, a second telescope at some other location looking at the same source and therefore seeing the same waveform passing it by. Okay? So the second telescope will see the same waveform, however, with a time lag given by the path length difference between these 2 telescopes. So therefore, if I correlate the photon counts seen at telescope 1 and telescope 2, I will see a peak in the cross correlation on the time scale given by this path length difference. And the width of that peak in the correlation is set by the coherence time of these envelope fluctuations, which before we saw is set by the bandwidth. Okay. So to give you a sense of the numbers, visible light has frequencies on the order of 10 to 15 hertz. Okay. And so if the bandwidth is also of that order, okay, then the width of this peak becomes femtoseconds. And so therefore, to notice that photons are coming to us correlated in time, we would have to be able to measure their arrival times with a precision on the order of femtoseconds, okay? Because if our timing precision were, say, orders of magnitude worse than that, we would never notice this peak in the correlation. We never notice that the photons are coming to us bunched together in time. Okay, so femtoseconds is really hard, right? If we were able to measure timing at the femtosecond level, we could just do normal interferometry at these frequencies, okay? So this is not doable, at least today. On the other hand, if we use narrower bandwidths, okay? So for example, if we use spectral resolution of like 1,000 or so, okay? Then instead of femtoseconds, we just need picoseconds. And picoseconds is good because today there exist these commercial off-the-shelf single photon detectors that provide picosecond timing. These are called SPADs. They're cheap nowadays. You can basically buy them on like websites like Amazon.com. Most of you have SPADs. So most cell phones have SPADs in them these days. Lots of your cars nowadays also have SPADs. Okay, yeah, so because these things are used for things besides astronomy, nowadays they are mass produced and cheap. Okay, right, so so these SPADs, so these high quality SPADs cost like thousands of dollars. They also come in arrays, nowadays. Okay, so therefore, thanks to these developments, measuring these picosecond widths is now doable. In fact, has been done. Okay, good. Okay, so how do these correlations look in practice? Okay, so again, for a top hat source, okay, this is how the 2-point cross correlation might look in the absence of any sort of noise whatsoever. Now, if we allow for photon noise, what does that do? It adds noise to this correlation function. Okay, and if we allow for timing noise, what that does is to smear out this correlation peak in the x direction. Okay. Good. So therefore, to maximize the signal to noise in seeing these correlations, we want lots of photons to minimize the shot noise, and we also want precise timing to minimize the smearing effect. Okay, good. So if you measure those correlations, what does this tell you? Okay, so recall recall we saw before that a regular interferometer, the visibility, which is the correlation of the E field, okay, right? So that measures for us the Fourier transform of the brightness of the sky. Here, instead of correlating the E field, we're correlating E squared. And so if you look at this for a moment or two, you can quickly convince yourself that this measures for us the square of the visibility, okay? So we're measuring the exact same Fourier transform of the sky with one crucial difference, which is that we're only measuring the amplitude of the Fourier transform. We've lost the phase of the Fourier transform, okay? Now, losing the phase is a big deal, right? So the phase comprises, at least half the information in the Fourier transform, arguably more than half the information in the Fourier transform. And so losing the phase is a big loss, okay? So therefore, then you might wonder, well, then what's the point of doing any of this, given that astronomers know how to do, normal, regular amplitude interferometry? And the answer, of course, is, is this, right? Okay, so recall what I said before, right? So the way this works is that we have multiple telescopes, and each telescope independently records the arrival times of the photons independently. So therefore, there's never any need now to physically combine light beams. And so now we have no restriction on how widely separated these telescopes can be. Okay, so therefore, this gives us a way to do VLBI across the Earth, but at visible wavelengths.
By recording photon times, you mean this time series of the intensity in each of the...
No, single photons. You're counting individual photons coming in, recording their times. Okay. Yeah. Okay, good. Oh, yeah.
What's like the data that you're gonna be creating with this per minute? And like, do we have the backends that can actually do that right now?
Yes, yes, and yes. So yeah, so the numbers to sort of have in mind is that for the targets I'll be describing, photon rates will be on the order of like million counts per second. Okay, so let's take like a 1 day observation. A day is 10 to the 5 seconds. So a million times 10 to the 5 is 10 to the 11 numbers. Okay, each one is 8 bytes. Okay, so like a terabyte per day. So nothing.
Per telescope or total?
Per telescope, that's right. Yeah. Yeah, so for each telescope, you just buy some little like cheap terabyte hard drive and then just bring it over to your correlator. Yeah. Right, you do not want to store the data as like an array of like 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, right? Yeah, right. You want to store it as, list of times. Yeah. Okay, again, right. This is a way to get visible interferometry at Earth baselines and therefore can provide angular resolution thousands of times greater even than the Event Horizon Telescope. Okay, so what's needed to do this? So first we need a lot of photons, okay? And that means having bright sources and or large collecting areas. We also want to have fast detectors, right? And as I said, these SPADs have picosecond timing. There's also this newer technology called SNSPDs that are even better. We also want to have narrow bandwidths, okay, as I said. So that means either observing line emitting sources, or more simply for a broadband source, just use like a grating or a prism to disperse the light into many, many individually narrow channels. Okay. So I want to stress that all of these exist today. Okay. And so therefore, not surprisingly, this sort of interferometry is demonstrated today. It's actually demonstrated back in the 1950s and 60s, but it's also being done today. Okay, so today there's like sort of two classes of observations doing this. Okay, so one group, so one set of people doing this, are these huge Cherenkov telescopes. Okay, so things like Veritas, MASS, HESS, MAGIC, right? All of them have demonstrated detections of this sort of intensity interferometry. It's also been demonstrated using these much smaller, like 50-centimeter telescopes. Okay, and what's great is that the signal to noise achieved by these little like piddling like 50-centimeter telescopes is just as good as the signal to noise achieved by these enormous Cherenkov arrays. And the reason is that these guys are using these fast picosecond detectors, whereas the Cherenkov arrays have been using PMTs, which have nanosecond timing. So when you see this, then the obvious next question to ask is, okay, what sort of science could we imagine doing if we had these, huge arrays like these Cherenkov telescope arrays, but now instrumented with and also capable of using these fast picosecond detectors? And the answer is that, yeah, you can do a lot, right? So there's like 10 million possible sources you can imagine targeting with this. So in this talk, I'll just talk about one possible class of sources, AGN, which is like just the most obvious thing to go after with this, okay? So I think people here know what AGN are, but in case there's like any students, okay, so AGN are just supermassive black holes that are bright because they're rapidly accreting. And yeah, there's a lot you can imagine doing with this sort of ultra high resolution imaging of AGN. Okay, so I'll be showing you some forecasts, next slide or so, okay, and so for those forecasts, we'll be making some like, fiducial, assumptions about, the observations that we have in mind, okay? So for those forecasts, so the assumptions I'll be making are a total collecting area equal to the existing CTA array, okay? So this is one of these Cherenkov telescope arrays. A timing precision of 10 picoseconds, which again is very mundane nowadays for these SPAD detectors, and also 24 hours observing time.
I'm a bit confused, I think. Is there something additional external that you have to bring in to actually be able to use this visibility square? Because if I think of the standard picture of, I have a field
Mhm.
and then I have its power spectrum and I throw away all the phase information. There are like infinite numbers of fields with very different phases and very different structures that have the same exact power spectrum.
That is correct.
And so I guess it's unclear to me what does it fundamentally mean to have very high angular resolution in this regime where you're having a lot of trouble actually resolving
That's
the
right.
structure of what you're looking at.
That's right, yeah, so as you say, there's many possible phases for the amplitudes that you've measured, and therefore many possible realizations of the image on the sky.
Mhm.
Nevertheless, there are certain quantities that you have measured really well. Okay, so for example, one commonly quoted example is things like sizes of your source. Those are generically measured really well just by the structure of the amplitudes as a function of baseline. Yeah. Also describe some other examples. Also, for certain kinds of sources, it turns out that, it turns out that the amplitudes contain all the information. So for example, for a source which is symmetric under this sort of rotation of the sky, the visibility is real. All right, okay, right. But just the thing to have in mind is that, so for like sparse arrays, the thing you're kind of getting is like the size or like the radial profile of the brightness emission. But I will talk about ways to improve on this at the end. Yeah, assuming a B-way lesson. Okay. Where was I going? Oh, yeah, okay, good, yeah. So for the forecast I'll be talking about, just have these sort of numbers in mind for the fiducial observing program. Okay. So for that program of like the CTA array, 24 hours, okay, for a bright AGN, you get SNR of thousands in 24 hours, okay? Thousands, right? So this is not just like barely marginally detecting the source, this is detecting it at a huge significance, right? So this is large enough that you can study these objects in great detail. You can measure many, many independent numbers describing these objects, okay? Right, so the picture to have sort of conceptually in your mind, is that we can do this like every few days, and therefore we can and therefore we can like imagine making like movies of these sources like evolving over time, right? So yeah, so with these sort of highly detailed measurements, we can do things like measuring the sizes, the radial profiles of these accretion disks. So it turns out that from microlensing, there's like a lot of controversy about the sizes, the radial profiles of AGN accretion disks. Here, we'll just image it basically, to get the actual structure just directly, without needing any kind of model. You can also imagine doing things like testing this AGN unification model because, people argue that like type 1 AGN and type 2 AGN are systematically different inclinations. You can just check that directly. Okay, right. So since I'm a cosmologist, so I am required by law to show you a Fisher matrix corner plot. Okay, so here it is. So this is okay, right? This is just showing forecasts of various different parameters. That could be attained with that sort of fiducial observation that I described. Okay, so things like the inclination, the radial profile, the size of the disk. Oh yeah, and this one's also interesting. So this parameter corresponds to the inner edge of the disk. So in these like really stupidly simple like Shukura-Sinayev disk models, this inner disk edge is supposed to be related to the innermost stable circular orbit around the black hole. And so just again, with these direct measurements, you can just check whether that's true or not. Okay. Good. Yeah, but again, though, the point with the points, which maybe is hard to see because it's blurry, is that all these numbers are measured really well with tiny fractional errors. Again, for that fiducial observation that I described of like 24 hours for, for this sort of source. Okay, so, right. So I want to drive home that this is like probably like the most exciting thing you could do with these sort of interferometers, just like directly making movies, like resolved movies of these black holes. Okay.
Is atmosphere a problem?
Good. So, yeah.
Refraction index, right? And the length of, basically the time of a black hole. I don't know how.
Very good. That's right. Yeah. So the great thing about this sort of interferometry compared to like normal amplitude interferometry is that because you're not sensitive to the phase anymore, you're actually highly insensitive to most of the things that astronomers worry about. Okay, So yes, the atmosphere does have one effect, which is what you said, which is that the time of flight through the atmosphere can fluctuate as the atmosphere fluctuates. And so, okay, right, and so you can, so you can compute this. And so looking for sources more or less straight up, okay, the extra scatter in time is about like 1 picosecond. Or looking near the horizon is more like tens of picoseconds. And so if you have like single digit picosecond detectors, you want to look mostly up-ish. Yeah. Right. But all these worries about like the phase of the wavefront that AO has to correct for, yeah, none of that matters here. Yeah. Which is why Hanbury Brown and Twiss were able to detect this using their terrible telescopes. Yeah.
So you said this fiducial telescope is like a CTA-ish thing. Does that mean it's also CTA baseline?
Oh, no.
Sort of across the area?
No, that's right. So here I think I assume baseline's on the order of like a few to maybe tens of kilometers. Yeah. Yeah, okay, good. Yeah. So to maximize signal to noise, you want your baselines to be chosen to sort of pick out the angular structure of the source of interest. Right. Okay, so the first sources that you'll target with this will be the brightest sources, right? Now, the brightest sources are also the biggest sources on the sky, right? Because to like lowest order, just imagine that like every source has like the same surface brightness. Okay, so the first things you'll go after are just the brightest and therefore the biggest, and therefore only need like a few kilometer baselines. And then once you've exhausted doing that, you can now have larger collecting area to do fainter sources, but those fainter sources will be smaller and therefore we want them on somewhat larger baselines. And you those sources, exhaust that, and just so on, just like steadily building out. Okay. What's next? Oh yeah, okay, good. So again, I'm a cosmologist, so therefore I have to at least pretend that there are interesting cosmological applications of this. So, okay, so I'll talk about 1 or 2. First thing that I'll mention is how to measure the Hubble constant this way. So for the AGN experts, this is obvious, okay? So for the AGN people, this is using, this method called reverberation mapping. For the non-AGN people, let me just describe what that is, okay? So for the cosmologists, there's 2 things you have to know about AGN that are important here. So first, the emission spectra coming out of AGN, they exhibit both broadband continuum emission and also bright emission lines. Okay, so some examples are shown here. Okay, right. So so these are showing some spectra. So like the y-axis is like the brightness. It's a linear scale starting at 0. Okay, so the continuum is somewhere down here, and the lines are like that, right? Okay, so just like insanely bright lines in these sources. The next thing you have to know is that AGN luminosity varies over time, and that's seen both in the continuum and also in the lines. Okay, and so one example is shown here. Okay, so this is showing the light curve for some AGN. This is the continuum light curve, and it's fluctuating up and down sort of randomly. And also the lines are also doing the same thing, as you can see. But if you look closely, you can see that the line variability lags the continuum variability. Okay, so these lags can be like days or weeks or months, depending on the line, depending on the AGN. And the reason for this is thought, is that the line emitting region comes from gas, which is much, much further out from the black hole compared to the continuum emitting region. Okay, so the physical picture that AGN people have in mind is that the continuum light illuminates this line emitting region, heating it up, and the way that it cools down is via this line radiation. And so therefore, these time lags of days or weeks or months, that tells us that the size of the line emitting region is like light days, light weeks, light months. Okay. Oh yeah, right. So this is a movie. Yeah. So right. This is just illustrating that fact. Yeah, there's a lag. Okay. Good. So now, how do you measure Hubble? Okay, so now it's obvious, right? So again, the time lags measure for us the physical size. Okay. So more precisely, you measure the Green's function, the transfer function between the continuum and the line variability. Okay, you measure the transfer function in seconds, and therefore tells you the profile in centimeters. Okay, and of course, interferometry easily resolves the angular sizes of these broadline regions because they are big. Okay, so yeah, good. So we have the physical size in centimeters, the angular size in angles. And so, of course, comparing the two tells us the angular diameter distance to these sources in centimeters. So again, not in h-inverse centimeters, but in centimeters. And of course, since these are line emitters, we also have the redshift. And then distance and redshift gives us the Hubble constant. Okay, good. So this is a purely geometrical method to get the Hubble constant. There's no distance ladder, no Cepheus, none of that stuff. Okay. Yeah. Okay, good. So how well can you do in practice? So here's another corner plot. Okay, so again, this is just showing error bars on like a bunch of parameters, most of which describe the structure of this broad line region. For the AGN people, knowing these numbers would be hugely helpful. Inclination, like the radial profile, stuff like this. Okay, for the purposes of cosmology, these are all just nuisance parameters that we're marginalizing over. For cosmology, the one parameter that's interesting is the distance, okay? And so again, for this fiducial observation, so for this example, AGN, okay, so you measure 24 hours distance to like a few percent. One interesting thing, here is that, so the error bars here are dominated not by the error bars in the interferometry, but instead by the, the uncertainties that I assumed for the light curve. And after we finished our paper, I realized that I was like stupidly, like overly pessimistic about the light curves. Okay, so here I assume that the light curves are measured to 30% errors. And then, later on someone points out to me that that's stupid because obviously, light curves, light curves can be measured to better than 30%. So for example, here, these error bars are much better than 30%. Okay, and so since these errors dominate the errors in the in that forecast that I'm quoting here. Okay, so almost certainly, the actual errors will be much smaller than this. Okay, well, let's just take a few percent. Okay, so what this means is that one source gives you a few percent Hubble, and so a few sources give you like percent Hubble.
How can you get any constraints on the actual inclination of the source? Because I thought that since you're letting go of the phase information, all you would be able to tell is the size of the.
Yeah, so that's the sort of like, story people tell, but no, that there is actual structure about, there's actual information about the non-circularity. So you have baseline's disorientation and baseline's disorientation, and comparing the dependence of the amplitude of the visibility on the orientation of the baseline tells you the inclination.
What are the closest AGN? Like what's the sort of redshift range where you would be able to actually get good measurements of distances to these AGN?
Good. So the closest AGNs are at like tens of megaparsecs, but you don't want to use AGNs that close for Hubble. And the reason is that the AGNs have peculiar velocity. Everything has peculiar velocities. Okay, so to get Hubble, we were combining distance and redshift. We assume the redshift is just coming from the Hubble recession velocity, but on top of that, there are peculiar velocities relative to the Hubble flow. Okay, so for tens of megaparsecs, that's a huge source of error. For the AGNs that we have in mind that are at like hundreds of megaparsecs, it's negligible. Okay, so again, with like a handful of AGN, you're getting percent level Hubble constants. And again, purely geometrically, no distance ladder, blah, blah, blah. Right, so why would you care about this? Okay, so for the non-cosmologists, you may have heard about this controversy that's been going on for the past 10 years now about the value of the Hubble constant. Okay, so we have these two different ways to measure Hubble. So one method uses a feature in large-scale structure called the sound horizon, and this gives a value of Hubble of like 68, 67, something like that in kilometers per second per megaparsec. Okay, and a second method that uses Cepheid variable stars, it gives a different value of like 73, 74 kilometers per second per megaparsec. So those two numbers sound very close to each other, 68, 74, but the errors are now so small that this discrepancy, is now going to be like 6 or 7 sigma or something, if you believe sigma. Okay, so this fight will never be resolved. Okay, these two teams will just go on fighting forever. The only way to resolve this will be to have some completely independent completely separate measure of the Hubble expansion rate. And as a theorist, of course, we would prefer to have a method which is understood from first principles. And so geometry, I think we understand from first principles.
When you say purely geometric, I mean, how do you worry about very systematic assumptions you've made about this region? I mean, you have a few parameters.
Sorry, I didn't hear you.
When you say purely geometric, I mean, how model dependent on how you're modeling the region of the AGN?
Yeah, that's right. Yes, we tried to marginalize over a bunch of nuisance parameters describing the structure of the broadline region. But again, the picture to have in mind is that you're just seeing an image of what it looks like on the sky.
You're probably assuming that you have like a point source in the center. I mean, what if it's not a point source?
Yeah,
I guess the
yeah.
issue is, the systematic errors
right.
due to your assumptions
That's
about the actual geometry of how things are illuminated, reprocessed, and so on.
Yeah, that's right. Yeah, yeah.
How did
correct.
you
So it
work
is
about
true that I'm
this?
assuming that the broadline region is tiny compared to the continuum region is tiny compared to this broadline region. Yeah, that's right. And so if its size is like 10% or something of the broadline region, that could be then one extra thing to worry about.
Because the statement here is that the.
Oh, but I should say also that we can measure the size also of the continuum region as well, because we'll have interferometry of that as well. Yeah.
Because implicit here is basically the statement that the physical size that you're getting from the interferometry measurement is comparable or the same as the slight day distance from where you got the reverberation mapping measurement.
And that is true because we are seeing the same region.
At the line.
We're seeing the same photons. It's the exact same photons in the light curve, same photons we're seeing in interferometry.
But this is because you have this narrow bandwidth centered at the line that you're looking at already.
Oh, so I mean, right. So as I said, the way to do this is that you'll have a spectrum,
Right.
and for each channel, you're doing interferometry independently. Yeah. Okay. Ooh. Right. Good. Okay, so I mentioned peculiar velocity just now as a source of noise in measuring Hubble. But one man's noise, of course, is another person's signal. And for a cosmologist, peculiar velocities are actually much more interesting than the value of Hubble. I mean, the value of H0, like no one cares, it's a number, right? Whereas peculiar velocities contain lots of information in them. Okay, so what I mean is that, right, so the line of sight component of peculiar velocities, that gives us these like redshift errors that can then mess up, our Hubble constant. They also produce redshift space distortions. The transverse components, they give us proper motions on the sky. So how large are these proper motions? So if we take a typical peculiar velocity, like a few hundred kilometers a second, at some cosmological distance of like a few hundred megaparsecs, this is like some fraction of a microarcsecond per year. So that's a tiny proper motion. It's so tiny that no one ever worries about this. This is so small that it doesn't affect anything. Until you have visible interferometry across the Earth, okay? So for these sort of resolutions, measuring this now becomes an interesting prospect. Okay, why would you care? If you can map out the velocity field around us, like the velocity power spectrum, right? This velocity field directly measures for us an unbiased measurement of the growth of the matter field, i.e., it's an unbiased measure of the matter power spectrum. Right, so of course, an unbiased measure of the matter power spectrum would be hugely useful for many things in cosmology, like neutrinos, primordial Gaussianities, dark energy perturbations, just like all these things that we care about, okay? They would all be helped enormously by a direct unbiased probe of the matter power spectrum, the matter field. Now,
For density that you expect to be.
good.
This be the bright AGN spectrum, right?
Very good. So, for the CMB people who have seen the KSE effect, the same miracle that happens in the KSE happens here. So for everyone else, the great thing about this is that when you reconstruct the matter field from the velocity field, the noise in the reconstruction is smaller or can be orders of magnitude smaller than the shot noise in the tracers used to do the reconstruction. Okay, so I'll say that again. The noise in the reconstruction can be orders of magnitude smaller than the shot noise in the tracers used to make that reconstruction. Okay, so what that means here is that we don't need a huge number density of sources to get interesting measures of the matter power spectrum. Or conversely, if we just use like all of the bright AGN that are there, we can get really incredibly precise measures of the matter field, okay, around us. And then, of course, that would be hugely helpful for many, many different applications in large scale structure.
What is the proper motion of that?
Sorry, I didn't hear
What
you.
is the size of proper motion?
Oh, yeah, good. So as I said, okay, right. So if you just plug in some numbers,
Do you have the reference?
do I have a, good. So, okay, good. Yes, so here I'm not trying to measure absolute astrometry. What I'm trying to do is to measure the relative proper motions between different, two AGN, yeah. Yeah, so normally this sort of wide angle astrometry is really hard, but we have a way we think of doing it. Okay. Good, so this would be much more interesting for cosmology than Hubble, but of course people like it. Okay, so hopefully you've all seen that there is just a huge slew of possible applications of having nanoarcsecond imaging. I mean, obviously nanoarcsecond imaging would be hugely useful. Okay, so what's needed to do this? Okay, so as I said, again, we need precise timing, also large collecting areas. Now the timing, as I described, this is now a solved problem, right? These SPADs are cheap. They're also like cheap to operate, right? So these really good SPADs, they operate at like -10 Celsius, which in Canada is basically, room temperature. The large collecting areas you might worry about, okay? Because if you want to do like arrays the size of these Cherenkov arrays, building telescopes that big might seem daunting. But of course, these Cherenkov people did this, and so how did they do it? Okay. So the reason why this makes sense, is that for this application, we don't need good telescopes. Okay, so what I mean is the following. Okay, so normally for an observation, for a professional astronomy observation, you want the surface of your mirror to be a parabola in shape, right? And the errors that you can tolerate are usually, something which is much smaller than the wavelength of the light that you're observing in. Okay, and so for visible light, with mirrors, you want the surface of your mirror to be good, to nanometers. Okay, we don't need anywhere near that for this application. Okay, so for this sort of interferometry, all we care is that for our mirror, okay, all we care is that no matter where a photon hits on that mirror, like here, no matter where it hits, all we care is that those photons reach the detector at the same time. The same time within the precision of our timing measurements, right? So our SPADs give us picosecond timing, and picoseconds times speed of light is millimeters, okay? So for this, all we need is mirror surfaces that are good to millimeters, not nanometers. Now, if you look at these like famous schematic plots of the amount of work, the amount of time that goes into manufacturing a mirror, all of this horrible grinding and polishing and thinking off single molecules using ions. Okay, so all that stuff is all done to get down to these nanometer surfaces. If all you need is millimeter surfaces, well, the mirror blanks come from the manufacturers already with surfaces that basically good enough. Okay, so in principle, this can significantly reduce the amount of work, and therefore cost required to manufacture the arrays that we're interested in.
And such a telescope would be only useful for this kind of application and nothing else. So you're thinking.
Good, so therefore, I am now not competing with other idiots to do observations, right?
But maybe it's easier or cheaper to buy observational time in some already built telescope than buy a new one, even though it's cheap or not.
Okay, so for EHT, for example, do they get all the time on ALMA? Do they get all the time on SB? No, they don't. Right, so yeah, it's a huge scheduling problem for them to get time in all the different facilities that they want. Yeah, so one could imagine trying to do this on VLT, on KEGG, on these existing 10-meter telescopes, and we'll get like 1 hour every 5 years or something, right? Because you need all of them observing at the same time. I think a much better strategy just is to build something dedicated.
You can still use them for this high energy neutrinos and cosmic rays. Channel telescopes.
I mean, you could, but why would you care about something like that? Well, you can do nanoarc-second imaging.
Well, not of cosmic rays, not of neutrinos, right?
Sorry?
Not of cosmic rays, not of neutrinos.
Oh, sure, but again, you can do
Extra, you know,
10 million possible
multi-messenger
astronomers
astronomy.
work. Hope you heard about this.
Is it the same kind of errors then in both of the cases?
Huh?
Like the, because I thought that like Cherenkov arrays were just some like buckets of water somewhere, right? That's not where you.
No.
Oh, so they have multiple kinds of detectors.
These are
Yeah.
air
So here I'm talking about, are these light buckets that are just looking for the air showers on the sky. They're seeing visible light on the sky from the air showers. Yeah. There's also things that are actually looking for, like the cosmic rays, like
Going through the water, observed.
Right. Yeah.
But they also have these Cherenkov telescopes as well.
Yeah.
Oh, okay.
So here what I mean are those, yeah. Right.
So for millimeter area of the surface, then the image of the star will be very blurred, right? Is there a concern that the
Yeah,
light
good.
from
So
the
good. So what? Yeah, good. Yeah. So right. Yeah, you're right. That'll be somewhat defocused. And so what you want to avoid is that the sky background over that defocused area
Yes.
is brighter than your source.
Right.
So again, we're first going to be targeting like the brightest things on the sky.
So that's 12 magnitude.
for example. And so yeah. Right. So typically this will not be a concern, but eventually, if you imagine going after even fainter and fainter things, eventually at some point that'll be a concern.
So what's you mentioned this like 1,000, SNR detection, I think it's like meter or so collecting area across the base.
Oh, good. Yeah. Sorry. Yeah. Good. Yeah. Sorry. I didn't say. Good. Yeah. So, okay. So the CTA array is something like 1,000 square meters. Okay. So for this, you don't care okay. So all that matters is the total collecting area. You don't care if that's like a few huge light buckets or instead if it's like a large number of small things, right? For that, you don't care. And if there's time, I'll describe other things for which you might care. Okay. Good. Right. So I talked about how using reasonable array sizes, we can get high SNRs even for extragalactic sources. Okay. So not just like Betelgeuse and Sirius, but like extragalactic sources using reasonable array sizes. So then you might wonder, well, okay, what could be done if we had more unreasonable array sizes? Okay, so suppose we had like staggeringly large arrays. Right, so so my dream is just to cover Canada in these like charitable telescopes. If we had that, what could we do? Okay, so first of all, most obviously, having bigger collecting areas, we could do fainter targets, and there's an infinite number of fainter things that would be exciting to go after, like obviously supernovae, tidal disruption events. We heard about photon rings the other day. Photon rings are easily resolved using visible interferometry across the Earth. Right. So all that, of course, is super exciting. Yeah. I mean, those things also like astroseismology. I mean, just like many possible applications. But what I find more exciting though is that when you have really, really big arrays with lots of different baselines, they provide qualitatively new information that's not present in these more sparse arrays. And so, what I mean by that is the following. Okay, so before I recall, I mentioned how, intensity interferometers, they measure the amplitude of the Fourier transform, they lose the phase. Okay, so it's long been known that when you can densely sample the Fourier plane, you get back basically everything that you lost, okay? So an example is shown here, all right? So suppose that this is what the sky looks like, okay? So we Fourier transform this throughout the phases and then try to reconstruct what the image was only from the amplitudes of the Fourier transform. Okay, so here I'm using a reconstruction method from the 1970s. Okay, so this method it's iterative. Okay, right. So you're right. So in this method, you make some starting guess, then you apply some algorithm where you iterate again and again and again. Okay, so you use convergence. Okay, so here, okay, right. So here I made this starting guess, right, which is just like some random field. Okay, then I did several 100,000 iterations. Okay, yes, that sounds terrible, but that ran on this laptop, so it's not so bad. Right, and then after several 100,000 iterations, we converge to this, okay? And you can see that we've gotten back basically all of the information that was present in the original image, despite not having the phases of the Fourier transform, okay? So this problem is called phase retrieval. And again, this has been known since like the 60s and 70s. So this sounds amazing, right? Okay. Now there are some drawbacks though to this procedure that I used here, okay? So first of all, right, so these methods are slow, right? And so I said that I had to do several 100,000, iterations on my core laptop. It suffered, but it was okay. Also, these methods don't do great, except in like the most optimal conditions, okay? So this example was like zero noise, like extremely dense sampling on the Fourier plane. If you violate any of those conditions, right? So if you have noise, these methods can do badly. So for example, these methods really easily get stuck. These methods can get these methods can get stuck in local minima, for the loss function really easily. Even sometimes, these methods, they can go uphill instead of downhill for the loss function. So what these demonstrate is that the information is there, okay? But the algorithms that were developed back in the 60s and 70s, those can be improved perhaps significantly. And luckily, oh yeah, Stephen.
Can you just re-explain again how this works? You get a lot of amplitudes of as many Fourier modes as you want, and you can somehow produce the phase structure.
That is correct. And it sounds like magic, right? So what you're doing is to make some assumption about the structure of the source. So here specifically, the assumption that's being made is that the image is positive. Okay, so therefore no negative pixels. And also that it's compact in the sense that the light comes from like here and not like here. And those are the two assumptions that are being made in this method. The positivity, of course, is a lot, right?
Yes.
Because if I just pick random phases, every image I'll make will have some negative pixels.
Right.
Yeah. Okay, good. So anyway, so this demonstrates that we can recover everything more, okay, given enough sampling. But the precise implementations can be improved. And so fortunately for us, these modern machine learning methods, they just completely destroy for this problem. Okay. So an example is shown here. Okay, so here I'm showing phase retrieval, but now using machine learning methods. Okay, so the method that I used for this example here, okay, that method is this HIO method from the 70s. Okay. And so you can see that it's amazing, right? I mean, getting this level of reconstruction would be fantastic for us, but also you can see that it's gotten stuck in local minima in all these cases. Okay, in contrast, so these machine learning methods, right? So they're not iterative. There's just like one shot. They just give you the answer back. And you can see that it's doing this well. They also do much better in the presence of, significant noise. And so with BA, we're also exploring, how well these things perform if we have more sparse sampling in the Fourier plane.
If you gave this a fuzzy image of like a car and not a person, would it just completely fail because it's been trained on images of people?
So this is good. This is always what everyone objects whenever people use the word machine learning. Like, oh, I trained on faces, so of course it's going to give me a face. I trained on cats, of course it's going to give me a cat. Right, it's always the worry. And again, this example demonstrates that is not true. Okay, so here I didn't use any 1970s machine learning method, right? I did this, this deterministic algorithm, right? There's never any training of Pikachu or Bulbasaur or anything, right? Okay, it got it back, right? So in the limit where the SNR is high and the sampling of the data is dense, okay, the posterior is dominated not by the prior, and instead by the likelihood. That's true for machine learning, it's true for all inference, right? So all you need just is to have a high enough SNR that no matter what your prior was, you're still getting back an actual image.
But in the noisy case, it's not necessarily true, right? In the noisy case, then basically you have two.
So for low SNR, that's right. There will be multiple solutions, and these methods, they give you samples from the actual posterior.
Right, so I guess in the noisy case, it's like some algorithm of denoising, right? The machine learning tool.
I wouldn't call it.
On some.
I wouldn't call it denoising. I would say that it's a way to get samples of the posterior. And so in the noisy case, the posterior is broader. That's all it is. Right.
But if your prior is very narrow, then you can maybe still get it very narrow.
Of course, and that's true in all inference, right? So
Yeah, so then.
If my prior doesn't include the truth, no matter how good my data are, I will always get the wrong answer, right? There's nothing different in this aspect about machine learning, right? Of
No, I
course,
mean,
you want to
this
have a
is-
sufficiently broad prior.
Right, but this method is just, the prior is very, very broad. Like,
Yeah.
But if you train on phase, for example, or some natural images, the prior there is very strong, you have a lot of sparsity, information.
Good.
I guess
And so
the
the
question
EHC
is
has some
whether-
examples of this, right? So they have these like famous paper where they, where they trained on like celebrity faces and they apply that to their reconstruction and at low SNR and at low density, they get faces back instead of accretion disks. And, right, and as they then dial up the density on the Fourier plane, as they dial up the SNR, then the faces turn into accretion disks, right?
That's a noisy thing?
Yeah, these are actual UC observations. Wait, like, I don't understand what you're asking then. I mean, obviously all this is done in the presence of noise. Yeah.
Yeah, I mean, I don't think it's like super unfair to complain just because you see this a lot in machine learning methods where like the population that you give it to inform it, unless you construct the network, like unless you have constructed whatever schema this is to, in the limit of, in some limit recover this algorithmically, right? It is not clear that you're gonna generalize to outside of what you've trained this on.
No, so I don't want to recover this algorithmically because as I described, these methods have a lot of drawbacks. Right, what I would like is to just have actual samples from the true posterior.
But the prior is like the training data that you give it is implicit in the prior that you're.
And of course, for any Bayesian inference, the prior you start with is going to impact on your posterior. So the strategy in generally, the strategy you want to adopt typically is, is to have a sufficiently broad prior initially, just to make sure that you're not tricking yourself. Right, and then once you demonstrate it on like high FNR. Okay. Okay, yeah, we can talk more, yeah. Yeah, I think that people just think that machine learning is like some terrible black box and it's just giving you what you put in. I disagree, but yeah. Okay, but the reason I'm showing this is that when you can do this level of reconstruction, i.e. this level of phase recovery, okay, this level of getting back, the actual data, then intensity interferometry is just interferometry, i.e. this is just imaging. But now it's imaging at the nanoarcsecond level. Okay, so far I've only been showing you these like super simple, like smooth sources, like these like Shapura, Semyayev disks and so on. But when you can do this level of reconstruction, we can now do arbitrarily complicated sources. Okay, and so the aspirational target I want you all to have in mind is that, okay, so suppose that we fulfill my dream of covering Canada. We could just imagine just staring at some like binary black hole, just like watching it orbit itself, producing all this incredible physics, all this, beautiful dynamics. Okay, so since I'm getting glares, I will stop. Okay, let me just summarize. So intensity interferometry, this is a way to do very long baseline interferometry across the Earth, but at visible wavelengths, and therefore getting orders of magnitude higher angular resolution. This does not need any new technology development. All of this stuff exists today. This has all been demonstrated today. Okay, using reasonable array sizes, i.e. things that exist today, you can get SNRs of thousands even for extragalactic sources. It's not just Betelgeuse. Okay, and there's many obvious applications for AGN, and obviously there's 10 million other applications for things besides AGN. Okay, so I'll stop there.
One question since we've had one.
How does the SNR do with time of observation? And you said like
Square roots.
square root.
Yeah, it scales linearly in the number of photons and linearly in the brightness of their source times collecting area, and 1/4 square root in observing time. The thing that matters is observing time divided by the timing precision, all that square rooted.
I'm thinking about not extragalactic things because they're boring, as we all know. But if you look in the galaxy at things like, I don't know, accretion disks, I mean, they're much closer, so you can again resolve them as well.
So things
But
like
the
X-ray binaries?
X-ray binaries or, cataclysmic variables.
That's something
Those are
for
nearby.
sure, that will be a good.
But they have orbital periods of, let's say, hours to sometimes tens of minutes.
That's right.
And in this case, so obviously, the image will be changing on this time scale.
That's not a problem, right? Because you know what the orbital period is.
Right, you do.
Right, so you also know when every photon came in. So now you just phase.
You need to have a model of the source and take into account the total motion.
You have to know the orbital period. That's right. Yeah, once you know the period, you can now just stack on this phase, this phase, this phase in the orbit. And therefore make a movie of this thing as this orbit.
Well, but what if object is changing? If there is.
Yeah, that's right. If it's
outburst,
recessing or something, yeah.
Dwarf nova outburst happening in the source, which I want to resolve how it propagates through the disk and so on.
Yeah, no, that's right. And people have been talking about this CV, which is like supposed to go off this summer or something, right? This like T Coroni Borealis. Have you guys heard of this?
I don't know, I mean, cities go off all the time.
Yeah, but this one goes off like 80, every 80 years, and this summer's supposed to go off. Last time it was magnitude 2, right? So it was like one of like the brightest things on the sky. And so people have all been waiting for this thing to happen. And yeah, just like resolving it as it's exploding would be like.
Oh, you're thinking about nova. I'm talking about dwarf nova is like an instability in accretion.
Okay.
That's, it's not, I mean, it's a big jump in magnitude of the whole system.
Mhm.
It's different from nova.
Okay, but for sure, things like CDs would be great targets. I think X-ray binaries might be hard.
Because it's too far.
No, because the black hole is like next to this like really bright thing.
Oh, right.
And the photon noise from the bright thing can swamp your target you care about.
It doesn't have to be a bright thing. Low mass X-ray binaries have, low mass companions from which they feed the stuff. It's high mass X-ray binaries that have very bright companions.
Okay.
This is probably
But who dominates like the photons that you're seeing, like the star, the donor star or the
I'm not sure in the optical actually.
Okay.
Probably it's still donor star, but I'm not sure.
yeah,
Definitely.
definitely hard. Yeah.
Yeah, okay.
Yeah. Planets I think will also be hard for the same.
Yeah,
Because unfortunately planets are next to these like really bright things.
Yeah.
But besides planets, I think there's 10 bajillion applications, yeah.
We can ask Neal more questions during lunch. Thank him again.